As we begin with section 2.2, we're going to be moving away from just looking at quadratic functions and look at polynomials as a whole. Reminder, of polynomials, anything to the form, ax to the n plus bx to the n minus 1, and it kind of trickles down. So we've seen quadratics, we've seen cubics, and we're going to see polynomials of higher degree. We're going to kind of allow it for it to be any degree. Now, I want to talk about a few of the properties that these polynomials are going to have. Look at them, what they're doing graphically, and then we're going to break down kind of a few different things on how to make them, how to find them, how to work with them. First, on the top of your first page, is this idea of being continuous. So polynomials are always continuous, which means no matter what that polynomial is doing, it's going to be one continuous curve rather than what we saw with the piecewise functions or step functions that kind of had these breaks. So if it has anything with this jump, this is discontinuous. We're not going to be looking at that. All of our polynomials are going to be nice continuous curves. They're also going to be smooth and rounded curves. So kind of like up here, it's going to turn and change, right? A couple of different turns in it might have. But all of them are going to be nice and smooth versus, say, something like an absolute value function that has that really sharp point. So again, we're not going to be dealing with anything that looks like this. Everything's going to be nice and smooth and continuous. And then I want to make one little note about the difference of, well, if the degree is even versus odd. Something that will kind of help us a little bit. We'll go into a little more detail on the next page. But for now, if we're given some polynomial and its leading term is x to the n, so we don't know what that is. We're used to quadratic, its n would be 2, cubic, n would be 3. Let's say it's 7 or n to the 19th or whatever it might be. A little note is that if n is even, it's going to look and generally act like a parabola, something quadratic. So, these either open up or open down. So if I maybe have something like x to the 8th, I can expect it to open up. If I had negative x to the 18th, I would expect it to look something like this and opening down. And to contrast that, if the degree ends up being odd, then we're going to have that it looks and acts relatively the same as something cubic. So if our degree is even, we're going to get a lot of similar properties as a parabola. And if it's odd, we're going to get a lot of similar properties as if it's cubic. And we could also deal with transformations, as we're going to kind of finish off on the bottom of this first page. We're just going to kind of look outside of our norm of dealing with quadratic or cubic. What do transformations look like? And the nice thing about it is they don't look anything different. So before we'd even deal with these transformations, let me get a different color real fast. If we were to just look at x to the 4th, we can assume, right, just off this first little note, it should look something like a parabola, maybe opening either up or down. So in red, I'm just going to do a very rough sketch of just x to the 4th, something quartic. Well, if you plug in 0, you get 0. If you plug in positive 1, 1 to the 4th is just 1, so we get the 0.11. Plug in negative 1, negative 1 to the 4th is 1. If you plugged in 2, 2 to the 4th gives you 16, so it's already shooting all the way up. And same with negative 2, shooting all the way up. So that real basic x to the 4th looks almost like a skinnier parabola, right? Because if it was quadratic, we would go over to up 4, but this is going to go over to up 16. Well, like I just said, transformations aren't going to be any different. We're just now working with a different parent function. So if I have x plus 3 inside that function, I know it's being shifted to the left by 3, which means I'm just taking this guy right here and I'm shifting him to the left 3. So we have that vertex, right? We can bring it over 3, and then we're going to have some similar properties. Now, same for 2 and 3. Give it a quick pause, give them a try, just off their transformations, and just off our little rough sketch of what x to the 4th is. see what you can do about matching up these other two transformations. All right, hopefully give it a shot. For number 2, we have addition or subtraction outside that function. That's telling us to bring this guy to down by 2. So we're taking our original down by 2. And we would go 2 to the right from there and up 16, so really up to 14, still out of our frame. And then same with the negative. We'll clean that up a little bit. And for number 3, 2 things going on, right? We have a change happening inside the function, but now it's -3, so we're going to go to the right by 3. And we got this 1/4 outside, and that was if we had a vertical shrink or stretch. That's going to be a shrink for us because it's a fraction in the front. And how's that going to be? Well, if we go out to 1, instead of going up to 1, we'll go up to 1/4. We go over to 2, instead of going up to 16, we'll go to 1/4 of it, so we'll go up to 4, and we'll start to look a little bit wider. But we also need to shift that over 3 to the right. There's where my kind of new vertex is. And then instead of being right 1, up 1, we'll be right 1, up 1/4, left 1, up 1/4. Instead of being right 2, up 16, I'm going up 1/4 of that, which is just 4. So 2 from there, up 4, 2 to the left, up 4. So it starts to look a little wider, a little more like a U rather than that point of a parabola. So these are going to be the general things we're working with polynomials. The nice thing is transformations don't change at all. So if we start to get more complex polynomials, we can still shift them around in the same way. But now we're going to do a little bit more focus on this idea of even and odd. Onto the second page, we're going to be going a little bit more detail with this idea of even and odd. And when we work with polynomials, this is typically our starting point right after finding out what degree it has. Our next step usually is looking at not just the degree, but the leading coefficient along with that. And that's going to help us decide that general shape of the graph we have just from that alone. And the idea of this is going to be called end behavior. And you'll see why it's called end behavior in just a sec. So remember on the first page, I said if we have some polynomial, a sub n is just our coefficient to that leading, the leading coefficient for it. X to the n, that's telling us the degree, so squared, or is it cubic, quartic, etc. And we made note that if the degree was even, that looked roughly like a parabola. But parabolas kind of came in 2 flavors, right? We either had where the leading coefficient out front was positive, so our parabola looks something like this, or that leading coefficient out front was negative, so we had that reflection, right? So it opened down. Now, I've left the middle of these two kind of blank for a reason. If it was quadratic, we know already to expect, right? Smooth curve, and that middle is a vertex. But think when we do cubic functions, sometimes we had that nice smooth S. And other times we got those peaks and valleys being created, a lot of those changes and turns, right? Well, as n gets larger than 2, so 4, 6, 8, etc., we're not exactly sure what's happening in that middle. It could be really smooth, it could have a lot of peaks and mounds going through there, but we do know for certain is that this end behavior is going to be opening up if a is positive in the front. It's going to be opening down if it's negative. So we know that it's going to be aiming into positive infinity on both sides and negative infinity on both sides if it's negative. And towards the end of the lecture, we're going to focus more on how do we figure out the centerpiece. But for now, we at least know how it's going to begin and how it's going to end with that end behavior. Similarly, if we have n is odd, we may know it looks a ton like something cubic. So here's that typical kind of S curve, right? If we had something cubic, but if a is greater than 0, so it's positive, it constantly is increasing. And if it's negative, remember, it gets that reflection. So that snake kind of went down and it was decreasing. Now, just like with these, we're not sure 100% just off this information. What's happening in the middle? Is it smooth? Is it bouncing up and down? But we do know that end behavior. So we can kind of leave that little squiggle in the middle, kind of saying we're going to get to that. But for now, we're just focused on this end behavior. So for here, it's falling to the left, rising to the right, and then be rising to the left, falling to the right. And this is always going to be that starting point on how we evaluate and build and graph and work with polynomials is, well, what's the general shape going to be? So we're going to give that a shot just looking at the end behavior of these next four problems. So as you look at 4, 5, 6, and 7, we'll do one at a time. We want to look at the left-hand behavior and the right-hand behavior of each of these guys. And what we mean by that is, if we were to look at one of these, is it either rising to the left or falling to the left? And then how about that on the right? So this is what it would look like graphically, and we're just going to kind of write it out on these. So looking at number 4, again, with end behavior, the only thing we have to look at is just that leading term, because that's telling us all this information. So for one, we have that n is odd for us, it's 3. So it's got to be one of these two cases. And then we have this 1/4. Normally we'd go, oh, it's going to be a shrink. We just did it on the page before, that transformation. But we're not worried about that. We're just worried about the general shape. Is this 1/4 something positive or something negative? Well, it's positive. So this graph right here of this polynomial is going to look roughly like this third guy right here. So we know to the left it's falling. And then to the right, it's rising. Now we'll do number 5. Number 5, again, it has now 3 terms, but we're only concerned about this leading term. It's x to the 5th, so again, we're dealing with something odd, one of these two cases. But if you look closely, there's a negative on that leading coefficient, which now has us dealing with this 4th case of it's constantly decreasing, but in terms of end behavior, the left side of that graph is rising. Let me fix that R. And that right side of that is falling. So again, a polynomial can have, say, 30 terms. As far as end behavior in that general shape, it's all coming from that very first term. So give it a quick pause. Give numbers 6 and 7 a shot. All right, hopefully 6 and 7 weren't too bad for you. Number 6. Again, we have 3 different terms, but I only have to worry about the first term, that leading term. That said, I could have rearranged the order. The leading term is always that variable that has the largest exponent on it, that largest degree. So even if this was out of order, I would have to find the one with the highest order. That said, x to the 8th, 8's even. So the general shape of number 6 has got to be something close to a parabola. But now we want to know, does it open up? Does it open down? We got that negative out front. We know it opens down, which means the left and right, those ends are going to fall. And for number 7, I forgot to include our f of x on that. But again, for number 7, 3 terms are showing up. That x to the 5th is that leading term, the highest degree. We look at our options of odd. It's either the going up with the S-curve, little snake, or down. It's positive though, so it's going to look a lot like this right here, that original cubic, which falls to the left and rises to that right. So as we'll see, when we start dealing with even higher degrees, if I were to give you a polynomial, say like this number 7, you could at least start knowing that the graph will have it falling down here, rising up here, which at least gives you some instruction or direction of what to be expecting in the middle a little bit, as we're going to see as we move on to the next few little sections. Once we've figured out the general shape of a graph of a polynomial, the next thing in line is to work with zeros and what we're now going to be calling turning points, which we've already kind of worked with. This is the relative max and min, and we're going to see a little example of that in a second. So once we get, say, the end behavior, and we know where it intercepts the x-axis, we'll be able to kind of tell a little more detail of the specifics of that middle region that we kind of skipped over on the last page. But kind of a few little things first. If we have some polynomial, so the basic one, x to the n, whatever the degree is, that's telling us the maximum number of zeros we can have. So I'm going to do, let's draw this up here. I'm going to do 3 kind of separate cases all in one graph of looking at something cubic. So the first time we see something cubic, it looks just like that. And it only crosses that x-axis once, right? So it has that x-intercept of 0, and it's kind of repeated 3 times. That's using up all 3 of our possible zeros. We could have another. It kind of crosses, comes down, just touches the axis, and then goes back up. And this would have 2 possible zeros. And then a third one we could have is if it goes all the way up, comes all the way down, and all the way back up. And that gives us a possibility of 3 zeros. So if we're dealing with something, say, cubic, it has at most 3 different options of zeros. You could have 1, 0, 2, or 3. Now, we've seen stuff like this before, but this idea of turning points is a little bit new. So kind of bring that back up. I'm going to redraw these, and we're going to talk about what it means to be a turning point. So a reminder, turning points are that max and min was a relative idea. So somewhere where we have a change from increase to decrease, or vice versa. And if you look at the basic case, say of x cubed, it never changed, right? It's always increasing. So it has at most 3 minus 1. So at most 2 turning points. But for the base case, it has actually none. Now, if we were to look at our second case, we kind of drew in. For the second case, in 2 spots, right, it goes increase to decrease. So we had a little max right there. Decrease to increase, a little max, or sorry, minimum right there. And where we make that change from increase to decrease or vice versa, where we make that turn, those are our turning points. And again, if it was cubic, 3 minus 1 is 2, you can have at most 2 of them. And even in that third case, I'll kind of draw that in too. Went all the way up, all the way down, all the way back up. It still only had 2 turning points, right? Even though it had 3 zeros, how many zeros you have is not going to be related to how many turning points you have necessarily. So, but this had a change from increase to decrease, so it had a max. Decrease to increase, it had a min. And again, at most 2 turning points. And we already knew that because 3 minus 1 is 2. So when we're looking at polynomials, that degree is going to tell us the possibility of times it's going to cross that x-axis, but it's also going to tell us the maximum number of changes of direction we can have from either increase to decrease. We'll be using that in just a sec. And I just want to make note on this following down here. We're going to see a lot of this kind of throughout the rest of this chapter. These following 4 statements are equivalent. So if I say x equals a, if I say it's a 0 of a function, well, where'd you get the zeros? That's when you let f of x equal 0. So that's no different as that being a solution to it. And then right here, that's no different than we just have a factor of f of x being x minus a. That's typically how we find them, right? Typically, we let f of x equal 0, we factor it, then set each of these equal to 0 to get that 0. And again, graphically, that just means the point a comma 0 is an x-intercept of that graph. So we're going to use kind of these tools that we already know how to do to find zeros. We're going to do those for number 8 and 9, but then we're going to bring in this idea of turning points. I'll do some quick sketches on the side too to kind of help us make some sense of that. So looking at number 8, first thing we'll do is want to find zeros. So we're going to let f of x equal 0. We let it equal 0. We can factor out, I'm going to factor out actually a -2. So we're going to have -2 and also an x squared, leaving an x squared and then inside -1. Now from there, see if we recognize it for some of us. Can't do anything else here, but this is ultimately a difference of squares, so we can actually do just a tiny bit more than that. That's x plus 1, x minus 1. So now these factors of our original function, if we set them all equal to 0, those are going to be solutions to that. So that's no different than we typically do. Set each of these equal to 0. So here, no matter what we do, right, we divide by 2, get 0. Square root of it, we get 0. Subtract 1, we get -1. Add 1, we get +1. So we have our 3 zeros. But what type of function was this? This is a polynomial. The degree was of 4. And we just saw we should have at most 4 zeros, but it doesn't mean we have to have exactly 4 zeros. So we have something quartic with only 3 zeros, and that's totally fine. But now we want to talk about turning points. So if we're talking about turning points, that's going to be your degree. So that's 4 minus 1. That tells us the maximum number of it, which gives us 3. And I'm going to give a rough sketch of roughly what we know so far. And then we're going to get into detail how we can do this more accurately on the next page. So if we, again, start always with end behavior, it's even, so it should act like a parabola. But it's also even and negative leading coefficient, so it should open down. So I know technically, and you don't need to do this part for this problem, I just want to give you an idea of how we're going to use these things. Technically, we know this thing opens down, but we don't know what's happening in the middle. But I do know some details, right? I know x equals 0 has to cross right there. At -1, it has to cross. And at +1, it has to cross. So the last thing we need is, well, when does it cross these versus maybe when does it just kind of touch that point and turn around? And that's going to be kind of what we finish off at the top of the next page. But for now, we're getting a good amount of information about this parabola, right? Or not parabola, the polynomial, right? We know it's quartic, so it opens down. It's negative up front. We know it has 3 different zeros. So we just need only a little bit more to kind of connect those dots. But that's on the next page. Moving on to number 9. Number 9, you guys give this one a try. Number 9, it's just something quadratic. So it should have at most 2 zeros. Again, quadratic, so at most, well, 2 minus 1 turning points, which is just 1. So we know our turning points is going to be 2 minus 1, which is at most 1 turning point. This one was at most 3. But give it a second. Make sure you're good at finding the zeros for number 9. Shouldn't have been too bad for us. This guy's set up nice as something quadratic. We end up with x plus 5, x plus 5, if we factor it. Well, that's just the same thing, right? So we could just set one of them equal to 0. Subtract the 5 over, we get x is -5. Now, although we've done a ton of graphing of quadratic stuff, I'm just going to do that same idea from what we just did above, of just using what we know now generally of polynomials to see what we could get on the graph. Well, it's quadratic, so it's even, right? Even polynomial is going to open up because it's positive out front. So my end behavior was to rise to the left and to the right. I'll make these a little bigger for us. And then I know I have specifically only one zero at -5. 1, 2, 3, 4, 5. So if we know it's opening up, and that's the only zero, we might expect something that looks kind of like this, with it kind of coming down in the middle and connecting, which we would know just from all of our experience of quadratic stuff. So again, little recap on this page. Even polynomials, the even degree, they open up like something quadratic. If it's odd, it has generally that F shape of something cubic. The degree tells you the number of the most possible amount of zeros, but you don't have to have exactly that many, right? For this guy, we're missing one of our zeros, which is fine. We'll see what that means. And same here with number 9. We're missing one of those zeros. We only intercepted it once, right? And it bounced. So we can use this to kind of not only find zeros how we normally would, but start to interpret what the rough graph of these look like. And now we just need to find out one extra bit of information. What is happening in between these zeros, and how do we figure that out? Before we dive into that last little bit we needed of what's happening between our zeros, our x-intercepts on a graph for a polynomial, we want to make sure we can kind of work in both directions. So when we had that little section that said the following four are equivalent, it's nice to be able to work in both directions, because being able to do that's going to help us analyze all these polynomials we're working with. And to do that, we need to be able to even create polynomials. So we did stuff with things quadratic. We just saw, given this information, write something in the vertex form or standard form for this quadratic function. We want to be able to do the same with polynomials in general of any degree. So how do we do that? Well, for 11 and 12, we're given the zeros of the graph, so I could graph them and we'll have it at 0, 1, 6. But graphing is not going to help create the polynomial, but that little section of equivalencies will. If I know these three are zeros of my function, then I know that those three are going to be factors of that polynomial. So x minus 0 is a factor, x minus 1, and x minus 6. So I know my polynomial has to be roughly of this form, right? Because it's equivalent to these being the zeros. Well, the nice thing about x minus 0 is it's just x. And then this guy we can FOIL. X times x, x squared, negative 6x, minus 1 more x, minus 7x. And then we add a 6. And then lastly, we can multiply this x in here, distribute it through, we get x cubed minus 7x squared plus 6x. Now at the top of your sheet, it makes note that there are many possible polynomials. So here's one. Here's the one we probably were all going to get for this one. But as a reminder, when you're finding zeros, and we've done this before, say we had fractions in our polynomial, how do we make that easier? Well, we cleared the denominators. So if we had any multiple of this whole polynomial, let's say multiply everything by 2, so 2x to the third minus 14x squared plus 12x. These two polynomials represent the same function. So having either of these will still give us the same zeros. It's just that this is the most simplified because our leading coefficient is just 1. So that's what it means, but there might be multiple possibilities in there. So this one wasn't too bad, right? We had that x minus 0. We had this other little bit to FOIL. Now we got number 12. Take a moment just to get the setup of number 12, just this first line. See what you can get for that. Just that f of x. What is this represented as? Factors. Hopefully you gave that a try. So before we go here, we're going to jump back here for a second. If the 0 is a 1, we have to remove that from x to create our factor. So our 0 is the entirety of this 4 plus root 3, and then the 4 minus root 3. So we have to remove the entirety of that from x. So here is one of our factors. Starts to get ugly, I know. And then we're going to do the same for the other. X minus, well, x minus what? 4 minus root 3. And let's have these brackets on here to kind of differentiate from that 0 itself. So now we're doing more or less that same idea over here. This one's just going to take a little more algebra intensive. So I'm going to get rid of the brackets. So I kind of want to just distribute these negatives through, just so I have one whole polynomial times another. So we're going to have x minus 4 minus root 3. And then we're going to have x minus 4, but then this time plus root 3. And now this just becomes a really big distribution problem, right? We'll distribute x all the way through, negative 4 all the way through, negative 3 all the way through, and simplify what we get. So that's what I'm going to do here. I'm just going to distribute this x all the way through this guy. So everything here gained an x. Now everything's going to gain a multiple of negative 4. And then lastly, everything's going to gain a multiple of negative root 3. So minus root 3x plus 4 root 3. And then minus root 3 times root 3. That just frees up 3, so minus 3. Super ugly, right? So it's not quite where we want it. Whenever we like to deal with polynomials we're given, we want it as simplified as possible. So we want to create one that's equally as simplified. So as I go through it, we're just combining like terms, see if anything cancels. Any other x squareds? No. Any other just x terms? I got an x term here with a 4, another negative 4x. But I also have the 3 root 3x, and I have the other root 3x. But the nice thing about this one and this one is that they are opposites, right? So those are just going to cancel out. So we just got this negative 8x. And we're working our way through. Now we just want the constant terms. So we got the 16, negative 4 root 3, another 4 root 3, and a minus 3. But just like with this other square root of 3, we see these two guys are just opposites, so they cancel out, leaving us with the 16 minus 3. And again, this is creating a possible polynomial. Given this, we would find these zeros. Typically, we wouldn't do this through factoring. We'd probably plug this into quadratic formula, hence where we're getting that plus and minus of that square root. So given a square polynomial, it's important to be able to pull information from it, but it's also important to get that information and create that polynomial so you know it all connects. Now we're going to include one last little detail for us. Then we can tie all that stuff together to be able to graph polynomials really of any degree by hand, which is a really important skill. So for starters, before we dive into that last little bit we need is on something called multiplicities. So as we saw in some of the last few problems, right, we found zeros, but something that should have had up to 4 only had 3, so kind of one was missing in a way. Well, that's coming from multiplicities. So if you have some factor, so I think we had, say you have a factor x cubed and then x minus 1, the power that that factor is at is our multiplicity. So for example, here, the first one has a multiplicity of 3. And this, it's not showing it right, but this is only being to the power of 1. So this would really only have a multiplicity of 1. And that multiplicity tells us what happens at that 0. Do we cross through the 0, or is that one of our cases where we just touch it and we turn back around? And that's broken into 2 different cases. If that power is odd, like we just have with those two, then we cross at that 0. So we're crossing through the x-axis. And if it's even, then we're going to bounce or turn around. Regardless, we're not going to cross. We're just going to touch that 0 and turn back around and bounce down to the other direction. So if the power of the factor is odd, we cross through it. If it's even, we bounce or turn around at that 0. And we're going to see some cases of that coming up. So now we tie it all together. To graph these polynomials, what do? Well, first, we want to know end behavior. So if we look at number 9, we look for the degree of 3. So something cubic. So down here on the graph, I know it's going to follow that S pattern, right, roughly. So I know it's going to fall to the left, rise to the right, and we can change the placement of those arrows in a second. That's just letting us know. And I know it's going to have that increasing because it's positive, it's not going to be reflective. All right? So next we want to find our zeros. So let's find our zeros. Looking at this guy, equal 0. I'm going to factor a 2x squared out. And then we set it equal to 0, right? 2x squared equals 0, x minus 3 equals 0. So x equals 0, x equals 3. Found our zeros. I'm just going to put them on our graph for us. 0, 1, 2, 3, 3. So either, right, that's not directly in line, so we can change the end behavior. But at least we know what to expect. After we find the zeros, we want to look at the multiplicity of each of these. So we want to look at multiplicity. For x equals 0, take a second and think what the multiplicity of that was. Again, if it's odd, it will cross. Even it bounces at that point. This x equals 0 came from the 2x squared. So the 0 of x, or the factor of x, was squared. So this has a multiplicity of 2, which tells me it's going to bounce. And our other had a multiplicity. It doesn't show it, right? But anything that doesn't have a power, it's really to the power of 1. This is a multiplicity of 1, so this is going to cross. So now I'm going to use those ideas and kind of just do a rough sketch of what's going to happen. At 0, something's going to come up here, right? And then it's going to bounce. It's going to turn around. And at x equals 3, I know it has to cross through. So I really just need to know now what's happening to the left of the 0 down here, and what's happening between these two, and then also maybe a little to the right. But I know it's going to go roughly up, bounce around at 0, come down to some degree, and eventually have to turn around and come back through. So that fourth thing we need to do is actually test some points. And we just want to test some points kind of around these zeros to see a little bit more of the detail that's happening. So I'll do a couple. I'll do f of -1, do f of 1 and f of 2 to see what's happening in the middle. And then I'll also do f of 4 to see how high is this jumping up? Is it kind of softening off? We'll also do f of 4. Well, if we plug in -1 into the original, we get -2 minus 6. So we get -8. So -1, 2, 3, 4, 5, 6, 7, 8. So it's coming down here. So we can now kind of change the details of this. We know it's coming down, but it's coming down a lot steeper than we originally kind of just sketched out. So it's starting down, turns at this. Now what's happening in the middle? F equals 1. You plug that in, you get 2 minus 6. You get -4. We'll do f of 2 at the same time. You plug that in, you're going to also get 8, which is 16, and then you're going to get -12. Sorry, not -12, 24. And so here you're going to get -8. So f of 1, we come down 1, 2, 3, 4. And the f of 2, we also come down here all the way to -8. So that's going to kind of change how steep these are a little bit, yeah? So it's going to come down, down, turn around, it looks like at this point, come back through, and then we need to see what's happening at f of 4. If we plug 4 in, we're going to see we get something up at 32. That's jumping way up out of the scene, right? But that seems to make sense with the flow of it. It's coming up really steep, and it's going to continue that. So what is that fifth thing right here? That fifth thing is to finalize the sketch. So again, we started with end behavior. The placement wasn't perfect, but we knew the general shape, right? It had to be that kind of S pattern of the cubic. We found and plotted the zeros. So we know where those zeros are. We then looked at the multiplicities to tell us, do we go through at that axis or turn around at that point? We tested some zeros in between, or sorry, some values in between, just to see what are the specifics of this. You know, is it dipping really low? Is it a little shallow? Get a little more detail in that sketch. And then finally, we're making those changes and kind of finalizing it. So now we have number 10. I want you guys to give number 10 a shot on your own. Again, just do it one piece at a time. Given the graph, see what the end behavior would be. Find the zeros, you can do that. Look at the multiplicity, and then test some points in between. So give it a little pause, give that a shot. All right, hopefully you gave that a shot, number 10. We'll come in and kind of work it together. Number 1, end behavior. Ultimately, it's a power of 4 for the degree, so something quartic. So it should look like a parabola, either opening up or down, roughly. Positive out front, so it should do something where it's opening up. It's rising to the left, rising to the right. And we'll deal with exactly where that's happening in a second. Next, we want to find the zeros. So you set this equal to 0, 3x to the 4th minus 4x cubed. Can pull that x cubed out. 3x minus 4. Well, then we have x equals 0, and we have x equals 4/3. So we'll graph our zeros. Here's 0. We'll do some bigger gaps here. This is 1, this is 2. So 4/3 being 1 1/3. Now number 3 on our list is looking at multiplicities. Our 0 of 0, this is coming from x cubed. That's multiplicity of 3. And again, if it's an odd multiplicity, it's going to cross. And for the 4/3, that's only showing up once, which means we're going to cross there as well. So we know if generally it's rising from the left, it's going to have to come down, cross. Something's going to happen between these zeros because it has to then cross back up. So now we want to test some points and see what's happening in the middle. So I'll do kind of 1 in between each of these, see what's going on. We'll do f of -1, f of 1, and f of 2. Kind of move this out of our way. We know this should be something like this. So if we plug in -1 into our original function, we're going to get 7. So at -1, we're going to come up 7. 1, 2, 3. So at -1, 7. So a little steeper than we first imagined, but we're going to fix that in our last step of finalizing it. If you plug in 1, we're going to get -1 out of it. So at 1, we're coming down just 1. So where this is kind of in line, right, this is going to need to smooth out a little bit, not be so steep. Then f of 2 gives us 16. So at f of 2, we're coming way up. So we're getting a lot steeper. So now we have our basics on the graph. We kind of want to make those changes and make those fixed so that it's representing it. So we know that this guy is coming through. It crosses at that 0. Now at the 0, when it crosses, it's going to have to make a little bit of a change down to this point. And again, we could have tested more points in between if we wanted to be more accurate. You know it's going to have to turn around because at 4/3 it's got to cross back through. And actually, it should be a little more steep than that, right? Because at f equals 2, it's got to get up to 16. So again, it's close to a parabola, but there's a little bit more variation happening in the middle down here. Now, the final thing on this idea of sketching these polynomials is this word right here of sketch. So if I say to sketch something, it should be to this degree. Shouldn't just be a quick S curve or just a U. We should have the zeros in behavior, some points in the middle, and kind of finalizing it. But it's sketch because, well, it could be a little steeper, a little shallower on those in-between points, and it's just based off how many points we test. If I were to say draw, we'd want it to be 100% accurate, and then we typically use the graphing calc for that, which we're going to be using for this last little section of the last little bit kind of application of dealing with polynomials we're going to look at for this section is that of what's called the intermediate value theorem. And this is one where graphing calc is going to be helpful because we're going to be dealing with some pretty small numbers and kind of testing for zeros rather than finding them specifically. So intermediate value theorem, you got a definition up there, which is sometimes hard to interpret. If you have a and b that are part of the real numbers, such that a is less than b, so let's say a are x values, so let's say here's a on a graph, here's b, and you're looking at a polynomial f, such that the y values for these two are not the same on this interval. So here's our interval, right, from a to b. So we're looking at just this little chunk. Well, then we know that f is going to be every single possible y value between f of a and f of b. And here's what we mean kind of graphically on that. If here's a, say down here is f of a, and if here's b, say up here is f of b, then no matter what the details of that shape are, the polynomial is going to take on every single possible y value, right? No breaks in our polynomials between these two values. Now, on its own, that seems kind of useless, right? You're like, okay, why do I care? Well, a big piece of graphing these polynomials is knowing where the zeros are. And we can actually use this to kind of approximate where we get some zeros. And here's how we know that. If this takes on every y value in between these two, then it has to take on specifically the y value of what? It has to take on that y value of 0, right? So if we're testing points on this polynomial, and we were to jump from, say, something negative up to something positive, then we know what has to be in the middle of that. Well, we know 0, or our 0 of the function has to be in the middle of that. So if we had some starting interval, and we started to narrow it down and narrow it down, we could get as close as we wanted to approximate what that 0 is just by knowing there was a sign change that happened. And that's roughly what we're going to be doing over here. So on this one little example, we got this polynomial, and we want to find an approximate 0. So that just means we want to kind of use this idea, and I'm going to be using the graphing calc to help us kind of compute it quickly, of testing for where we think a 0 exists, and we want to get as detailed as looking at things in the thousands place. So to start this off, I'll get your graphing calc out, go to y equals, get that function typed in there. You want to go to second table. So in table, hopefully you have it where it's set up where you get to choose the options. If not, you can do that under second table set down at independent, make it say ask. We want to go to our table, and we're just going to start testing some points. We're going to start at f of 0. -2, f of 1, -4, f of 2, -6. So we're slowly going down, down, down. So maybe we're in the wrong direction, but we'll test a few more. F of 3, we're now back at -2 again. So if this is our graph, right, we start lower, 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 and starting to come back up. We'll continue it. F of 4, I get 14. So I'm going to pause real fast. Again, we're just kind of testing random values to kind of see the trend that's happening. Because if we see anything go from negative to positive, or it could have been from positive to negative, we know 0 has to be in there. And we just kind of saw that with these last two. Somewhere between 3 as an input and 4, we change signs, which means we have a 0 somewhere in there. So we're going to get a little more detailed. So let's look at, say, f of 3.1, right? We'll start at 3, somewhere between 3 and 4. So 3.1, I get negative 1.039. Okay, maybe we can get something closer to 0. Ooh, f of 3.2, I get 0.048. That's a lot closer to 0. Nice. 3.3, I get 1.267. But we almost didn't need f of 3.3. Why? Well, let's look at the first two. It's a negative value and then a positive, which means, again, our 0 has to be somewhere between these two values. And now we're going to work our way a little more accurate. So somewhere between 3.1 and 3.2, we have a 0. So let's test a few values. Let's do 3.15. So f of 3.15, we get negative 0.5116. 3.16, we get negative 4.23, 4.023, 3.17. I'm gonna let us know, because really we're looking for the change of positive to negative, right? I know I get something negative. 3.18, still dealing with something negative. 3.19, still something negative. And for these, I end up with negative 2.917, negative 0.0. Oops. This one is negative 1798. Of 3.19, I start to get really close to 0, 0.0665. So it's looking like the closer I get to 3.19, we're getting closer to 0. So I'm going to go one more little bump, right? And I'm going to look around 3.19. So let's do 3.195, like right in the middle. So f of 3.195, we get negative 0.0094. Now, we could continue to test this over and over, but what this is telling me is, again, just from our original values, we knew we had a sign change. So somewhere between those inputs must be a 0. We did it again between these two inputs. There had to be a 0 because we had a sign change. And as it got more accurate, closer to 3.2, really, we started getting really close to 0. So we just checked it to the thousandths place. And ultimately, it's asking us to find an approximate, so not the exact, an approximate to the nearest thousandth. And without wasting our time testing it forever, I would say this value right here of x is approximately 3.195 is a pretty good approximation as we're getting increasingly close to 0. Now, we're not going to use this a ton in this class. You definitely will with things like stats and in calc and engineering and physics. But the main purpose of this tool is to find where we have those zeros and be able to approximate it without even knowing the structure of the graph. And we do all that by just knowing polynomials are continuous. And also, at any sign change on a polynomial, we have a 0. So that wraps up our 2.0.